for the introduction. Thanks for having me here. So I will change gears a little bit from hardware, although we are using all that stuff as well, but say a little bit what we are planning to do for the SKA. And we had a nice talk yesterday from JC talking about ASCAP, which is the Merchant Wide Field Array, which is our kind of small little precursor, and talk a little bit about the SKA, of course. So what is the SKA? Just a bit of a reminder. Hopefully everybody had at least a bit of a glimpse what that is. So actually it's two arrays, it's not just one. It's two, one in South Africa, the other one in Western Australia, at the Murchison Radio Astronomy Observatory, and to be built in a few years. I will give you the timeline at the end of the talk. So, and it's going to be built in two phases, and what we are talking about mostly right now is SK phase 1, because phase 2 will only happen if we are kind of successful with phase 1. And whether that's correct or not is to be seen, but it's pretty hard to get money without being successful, obviously. So just the scale of it, SK1 mid, which is a mid-frequency array, standard dishes more or less, about 200 of them distributed across an area of 100 kilometer diameter in South Africa, and the SK low part is dipole array, so dipole sitting on the ground, about 130,000 of them out in the desert, and 70 kilometer diameter area. So let me go to the next one here. Well, the acronym means square kilometer array. Now SK1 won't be a square kilometer, obviously, because we have only the phase 1, which is about 10%, maybe a bit less even, of a square kilometer. And it's not just one, it's actually two arrays. So it's a square kilometer arrays, we should call it. So the acronym is not quite correct. And we have to meet a budget which is very, very tight. It's 687 million euros. So this number is changing a little bit because of conversion rates, but altogether that's what we are supposed to meet, and that's really, really tight. SK2 will be several billion for sure, because this will scale up to several thousands of those dishes and across whole continents. So it's a huge, huge endeavor, but even SK1 is quite a challenge. We'll have two processing centers, one in Perth, one in Cape Town. The one in Perth is kind of established, so it's this policy center. Whether it's big enough or whether we can use it in the way we want to, that's still to be discussed, but at least that's the current plan. Each of them is around 100 petaflops plus LinPack, and that is really LinPack because we are calculating our whole thing on 10% efficiency across the whole system, and that means all I/O, everything. And that's pretty aggressive, I would say. So the real petaflop numbers is far lower than that, but that's what we would need to reach what we want to. Fully operational should be sometime in 2024, maybe, hopefully at least. But we'll start collecting data and do some early science, just like ASCAP is doing far earlier than that. Now, the lifetime of such observatory is about 50 years, so it's a very long lifetime, it's a very long data provenance lifetime as well of the final results. This is a scary plot, and actually scary just because of the plot itself. So this is a 3 times logarithmic plot. Has anybody seen a 3 times logarithmic plot ever? So this is one. So both the axes are logarithmic, but also the sizes of the bubbles are logarithmic. And what's shown here is actually 15 science use cases proposed for the SKA. And these are just made-up proposals, essentially, for the case when the SKA would be operational. Whether that's exactly what's going to be executed is a different story. Now, the interesting parts are those ones, the big bubbles. All of them are in the range of 10 to the 18, 10 to the 19 bytes, that's exabytes, right? And that's the output volume of each of those experiments, each of them. Okay, that's SK1, and so that's where we are sitting. Well, of course, we can't afford this with 687 million euros. So we have to see what exactly we can do. So let's go back and see what can we do. Now, this is just a kind of a interesting sketch of how the SK would look like. And you have on top here the SK Observatory headquarters in Jodel Bank. So that will be a nice building. They are building it right now. And then we have the two sites, SK Mid and SK Low, one in South Africa, one in here Murchison Observatory in Western Australia. They are running it independently mostly. And then we have the processing centers which are doing this SDP, which is the science data processor. And then in addition, we'll have those regional centers. Now, regional centers are pretty much known from the LHC, the Large Hadron Collider, CERN. So they have tiered data centers all around the world, and we are essentially planning pretty similar things. Now, what's happening there is what is being produced by the SDP is by far not the final data product. It's just an intermediate data product. Because the science has to do a lot more to actually get that out and produce the papers, obviously. And those regional centers are approximately the same size as each of those individual processing centers. So mid-frequency, low frequency, just a bit of a reminder what that is. So low frequency for us is around 100 megahertz, exactly 50 to 300 megahertz for SK Low. So this is FM band. Now, if you are in FM band, of course, you want to be as far as possible away from anybody who's emitting that or even receiving it. Because if you can receive it, of course, there's some emitter which is close by, obviously. But that's one of the problems. So what we have out there in the desert is this nice thing down there. That's the Murchison Wide Field Array. And we have quite a number of them out there in currently 5 kilometer diameter array, and that's producing quite some data. We'll show a bit more of that later. Mid-frequency is starting from those 300 megahertz essentially and going all the way up to several gigahertz. How many gigahertz exactly depends on the receivers mounted, but the dishes are able to go to 20 gigahertz. That's the plan at least. So again, we have precursors, and actually two. So the left hand picture is actually a rendering of the SK1 mid. Then we have the Meerkat precursor in South Africa. So they're building that up right now, and the ASCAP is heard yesterday already here in Western Australia. In terms of data rates, astronomy was always a bit ambitious in that thing. But SK is slightly different because we are now sitting right at the top of the data producers. Previously, we were always a bit below that, which is a nice place to be, but with SK, we'll actually pass that. So in 2008, so that's the VLT, very large telescope. This is the top picture there. We produced maybe a few gigabytes a night or something. It's not a lot at all. And that's maximum, but at the time was quite challenging, especially because that was actually all transported either through a satellite link with very high latency or on disks. Actually, we did a lot of disk transfers on that one. And then 2015 we had MWA, or we are using MWA now for quite a number of years. That goes into close to a gigabyte a second maximum. And that's what we're handling nowadays all the time. And I will show a little bit more about that. And SK will be around a terabyte a second total, both together, SK low and mid. What that means is on the X is actually petabytes a year in output. What this means is an exabyte a year total data rate into the system. So this is a comparison, and hopefully that gives you a bit of a perspective what we have to achieve. So MWA is what we are doing now completely. Is 1.4 terabytes now, 5 petabytes a year of products we are storing in POSI right now. ICRAR is 10 terabytes an hour, 5.5 petabytes a year data products again. And SK Low will be 1,400 terabytes an hour. So that's exactly a factor of 1,000 from MWA in a few years. And that's quite a challenge for us at least. That's the environment we're working on. So I'll just do that and talk to it. So the Shire of Murchison, that's where the Bullardi station is, and the dot there, the circle, is around where the telescope will be, and the two telescopes, MWA and ASCAP, are right now. Geraldton is the closest town, as JC mentioned yesterday, and we have this nice network link, dedicated fibers, going all the way from the MRO to Perth. Now, the interesting thing is the population density here. And this graph down here shows the population density compared to other areas in the world. The blue bar on the left is Netherlands. It's a good comparison because there's a low frequency radio telescope there as well. The green one, the next one is the world. Then we have Australia, Alaska, actually, the gray one in the middle. Greenland is the green one, of course, on the right. And then Murchison Shire, 0.002 square people per square kilometer. That's about 1 toe on a square kilometer. So almost nobody living there, which is good, and that's why we are there. And then we have this fiber going down, 750 kilometers. So this is a very busy graph. Don't look at it too closely. It's just showing the data path all the way from those tiles over to an online archive which is sitting in the computer room over there on site. And that's going with about 400 megabytes a second into this online archive. And then it goes over the 10 gig Ethernet link, dedicated link to the POSI center essentially, and straight away into the tape archive. But in addition, we are also transferring data all around the world. Actually, a lot of data to the MIT in the US and to New Zealand and to India as well. Now, this is quite interesting because the MIT on network is 20,662 kilometers away. That's about half a way around the globe. Now, what we are doing very standard is data transfers of all that data almost in real time, 350 megabytes a second. So the array is producing around 320 or so on average, with switching times and so on. So we are getting that over to the MIT almost in real time. So this is a typical transfer, and the different bars are actually the production rate at the MRO. That's the left one, the light green, and the peak here. So that's the production rate. Of course, it's not constant. And then we have a rate which is going into the online archive. That's the blue one, the next one. And then the dark green one, which is actually on the POSI center. And the rate at the MIT is the purple one over there. So you see, we are almost keeping up with the transfer. There's a dip here. And that dip is actually due to people starting working on the cluster at MIT. That's the only reason why we have that dip. But then we are catching up again and getting all the data over. So they are usually seeing the data after half an hour or so at the MIT, popping up. So SKA ingest rates are, as I said, about 1,000 times bigger than that, 400 gigabytes a second per site. And we have to support all kinds of things, multiple concurrent observing projects and data sharing between projects, and this very stringent capital operational budget limit. And that includes power, cooling. Cooling is very important, of course, out in the desert where we have more than 50 degrees sometimes. So it's a quite challenging environment. And then also in terms of maintenance costs. One advantage, at least partially, we have a very high data parallelism, and so we can actually spread that out fairly nicely on HPC environment. But the throughput requirements are quite enormous. So the data coming out of such an array is actually a Fourier transform of an image plane or many image planes. And what we have to produce is essentially between 0.2 and 10 teravoxels a second to produce the image cubes at the end. And that's just the range of images produced for the science use cases, for the different science use cases. So there's a part of a stream pipeline in the beginning, which is doing kind of data cleaning and that kind of stuff. Also a bit of calibration, and then there's a batch processing, which is doing batch processing of about 6 to 12 hours observing time altogether. So we have to do buffering for all that time, and then do the processing on top of that. All of this has to run about 23/7 or so. Not all the hours in a day, so we have some planned maintenance downtime, and we can make use of that. But in principle, radio astronomy can be done throughout the day, so there's no limitation from physics there. So we do produce a lot of data, obviously, and this is a challenge for currently existing infrastructures. But funny enough, in principle, we could do it now. The problem is only we had to pay something like $200 million, and then have a power budget of something which we couldn't afford at all. So the problem is really affordability. And SK is really about being affordable, both capital and operational. But everything is in change as well, and this is another challenge. So if I tell you about all these science use cases, we know exactly that will change. So those science use cases won't be stable. We will have to run multiple pipelines and multiple different ones. They will change dynamically. The hardware, of course, will change. As we know, recycle times are a few years, 3 to 5 years. So the platform will change, and the algorithm will change as well. So it does change everywhere, and we have to keep at least the framework stable, hopefully, and that's one of our big things we want to do. So we need to provide a pipeline to be able to develop that in an approachable environment. And one thing the SK is not an HPC problem, it's actually an MTC problem. And MTC, who knows that term? A few, very, very, very few. So let's explain that. It's a many-task computing and has been introduced by Raiju, Foster, and Shao, Illinois Institute of Technology in 2008, actually. It's a nice paper around it. It's very interesting. And what that means is you want to have everything, essentially. You want to have throughput, the whole throughput, and to compute at the same time. And that's really, really challenging to get both of that. And SK is the typical use case of that, so it's really an MTC problem. Compute intense and data intense. All right, let me just do that. And we have to maximize I/O at the same time of the flops. So I will just go through this. And first of all, why do we think we can actually reach the operations? Well, we know that, right? I will show a bit more of that. So I've actually updated that yesterday with the latest numbers, so it's all in there. We have these two plateaus up there, which everybody knows is Chinese computers. So we've used that second line a few times, the Tianyi 2, not the first one yet. But the interesting thing for us is actually this one. So this is now showing the first 10s, 50s, and 500s computer on the top 500 line. Now, where are we? This is for ASCAP, and that was planned when I started at ICRAR in 2010. So we thought we would get ASCAP in 2011. We didn't, fortunately, and we thought we would have SK1 in 2017. And fortunately, we didn't get that, because we would have required the fastest computer in the world, and nobody would have paid us for that, for sure. Now, this is the current situation. That's great. Looks much better. Unfortunately, we've boosted up the, or downwards, the efficiency. We are again somewhere up there. And hopefully, John can help us there, so we can push that down a little bit again. So that's the only reason why I'm showing that one. Else we are not too concerned about LINPACK altogether. I/O is much more interesting. So what we are doing is we're connecting a very, very big sensor network into MTC centers, two MTC centers over a very wide network of 750 kilometers, and memory to memory. So we're copying data from a memory kind of environment into memory of the MTC center, which is quite interesting, and not a lot of people are doing that. So we have quite some fun getting there. So we need to optimize the wide area network, the internal I/O, and the processing at the same time. If you have one of them, it's hard. If you have all three of them, it's pretty tough. So what we're trying to do is having everything triggered by data itself, and what that looks like is hopefully it is very loud. I will stop that, but you get the idea. So it's really those domino small little pieces. They're just flipping over and touch the next one, and then that's actually triggering the next step of processing. They're actually doing exactly that. It's not like trying to have an overarching control panel which is saying, oh, cool, you are ready, I can start now this process. You are ready, I'm starting now this process. We're not doing that. So we are trying to do something which is a pretty old concept actually in telecommunications. It has been used a lot. It's data-driven, but what that is doing is actually change of program logic. We are not trying to do that. So it's not exactly what we are doing. For the SK, we are sometimes changing the program logic according to what's coming out, but very seldomly, and that's actually an advantage. And so what we are doing is actually, rather than data-driven, we are calling this data-triggered, and the data triggering is really like these domino pieces. So we make data actually active in the process. And what we call that is Daluji. So this system is essentially a prototype of an execution framework for the SK, and there are quite a number around actually. And to explain a little bit the name, and that's shifted, sorry about that, but this is going from Mac to Windows. So this Chinese character means yield, and that's flow. So this is called the data activated flow graph engine, and funny enough, it's actually pretty close to this English word. The other thing we are trying to do, and that's part of this Daluji framework, is separating concerns. And the problem really is, and we heard that during the last 2 days a number of times already, there's a mismatch between expertise in the meantime. So we have people who are really good in doing algorithms, they know the domain, they know how to program things in their domain, but they are not really good in doing software engineering. As we know, all this Fortran 77 code, and I have seen a lot actually in the past few days even, is not really what we want nowadays in those systems. But that's containing all the knowledge, the domain knowledge. We have other people who know very good how to do software engineering, but maybe not HPC software engineering, which is a completely different thing. And optimization of those systems, that's even less people who can do that. And then going into the hardware and doing things like in the previous talk, we heard about optimization of interconnects and that kind of stuff. That's even further away from normal people. So we are trying to separate those concerns into the algorithms, the logic, and all the scientific part. So these are the astronomers in our case, but scientists in general, and have operators doing the parallelization. So try to map that onto existing hardware. And then we have HPC software engineers which know about how to actually write the code for certain platforms and optimize the parallel code. And then we have this I/O optimization and interconnect optimization, which are different sets of people, definitely. If you have one who can do all of that, that's probably exactly one. So it's a single point of failure for the whole globe, not for your center. It's not a good place to be in. Anyway, so we are trying to do this, and on the left side you see how we do that. So we have actually different levels of graphs to describe the workflow or the processing environment. So we have those logic graphs and physical graphs. The logic graphs and the template mostly, that's where the astronomers come in. So they are planning which part of the execution has to come after which other part of the execution, and we have modules to actually drive that. So it's a kind of a graphical programming environment. So that logic graph template is essentially a template to be used to do certain pipelines. And since they will change, you will have a change every now and then, not too often though. Logic graph is the next step. It's actually parameterization of that template. So depending on how many numbers of channels or things like this you are trying to observe, this will change the template to a more concrete description. And then you have a physical graph which is then mapped to the hardware, the existing hardware, and that's using hardware information to actually generate that one. And that's a bit before the actual processing executes. We'll produce the template, but it's still not containing the actual node addresses or things like this. That's the physical graph at the end. So in terms of when this is being done, it's actually on different timelines. So the logic graph templates are probably years before people are deploying or developing those and think about what they want to do. So it's a repository of those templates, probably of the order of maybe 50 or so, but not more than that. And then maybe months before the actual observation, staff astronomers come in and say, okay, well, we are turning that template to a real graph, logical graph, and that's actually driven by parameters the project primary investigators is putting in to the proposal. And then weeks to the observation, we'll have a translation stage, which is actually fairly expensive in some, it depends on what algorithm you're using to do that, into a physical graph template, and that depends on the hardware available or the hardware you think will be available at execution time. And then we'll turn the template into a physical graph, and that's just a few minutes before observation is starting, and deploy that. And then, of course, the execution stage. How does that look like? So this is our pretty ugly prototype, and we're just putting together a project for a few students to make that really nice. Again, we'll probably use existing things here, but make that all interactive. So it's a working prototype, and it's good enough for us, but it's definitely not good enough for people. But that's how a typical real logical graph template looks like. So this is something we are actually executing in terms of a standard workflow. So these are, and we have those constructs around here, cycles, so these are loops actually. They will be unrolled into a cyclic graph at the end. So this is exploding once you get there. So it's actually the physical graph for the previous one, but only a very small fraction of it. So in the full SK1, this will be about 50 million of these boxes deployed onto the HPC. And we expect to have about 6,000 nodes. And so the optimization of that is quite tricky. Scalability, that was one of our interesting things. So again, this is good, sorry for that. So we have executed this on T92 to go to on 500 nodes only, unfortunately. So we are trying to do that on a much larger scale, but we went up to 12 million of these small little execution drops. And the overhead here is in microseconds on the left side here. And we can make that completely hierarchical. So the minimum here, as you can see, is around a bit more than 3 microseconds per single execution. And that's just the framework overhead introduced into those 12 million drops to manage them independently. The difference between the red and the yellow is one is just one deployment manager. It's not controlling the processing, as I said before, it's just deploying it. And the other one is 5 of those managers. And as I said, it's hierarchical, so we can have multiple stages of that thing. And it's nicely scaling, so happy with that. So how does the SK look like? We are somewhere here. In about 12 to 18 months, we hope to have some preliminary stage of procurement and some rollout of infrastructure works. And we are in the middle of, well, actually towards the end of pre-construction design studies, and that's 120 million euros coming on top of those 687, because that's all contributed by the member states. Between 2019 and 23, we'll have phase 1 construction. Maybe that's going to shift half a year or so. I have still 650, I changed it actually. 687. And sometime before the construction ends, we'll think about starting construction of SK2 as well, so there will be an overlap between the two. And of course, you don't want to design out SK2 and have a limitation of the infrastructure, in particular from SK1, so you have to interrupt all the designs to make SK2 happen. So it's a logistical problem, actually. And with that, I leave you with the conclusions. We do have good progress from the precursors. We are learning a lot of, like we are doing data I/O, we are doing long-haul data transfers, distribution of data, but we are a factor of 1,000 away, so we have to learn a lot more to get there. And hopefully we can get a lot of help from you guys here, both from companies but also from other researchers to do these things. And I've heard a lot of nice things today and yesterday, so hopefully we can get some insight. Now this is running on TNE2, 66,000 of those drops only, and the reason why we are only displaying 66,000 is because else you wouldn't see anything here anymore. So all the changes from gray to green is when they are running correctly, and some of them are red, so they are failing. The system is actually able to handle that in a graceful way. Graceful, we are still losing the data, but at least we can continue to run most of the rest. And there are thresholds, and we can just say, okay, it's good enough. Good enough is always good enough, like John told us. And with that, I leave you. Thank you.